Let's continue our Chapter 23 study of thermodynamics with looking at entropy. So entropy, as we learned the last video, entropy is the measure of disorder or randomness. Okay, so if we look at these two examples, let's look at the ice cube first. Ice cube is a solid, and we know that as a solid it is very organized. The structure is very fixed. The atoms are in just the right place. This is going to have very organized bonds, which means that the entropy is going to be very low on that. Remember, entropy is the measure of disorder. As we add heat to it, or energy, in other words, as enthalpy is increasing, it's going to create a liquid form or a puddle of water, which means that the organization is going to be much less, maximizing entropy. So we're going from minimum entropy to maximum entropy. And if we look at this jar of jelly beans here, this beaker, where it's very, very organized, is not very random. Okay, this has very low entropy, as opposed to the beaker on the right, where everything is kind of mixed and random. You stick your hand in there, you don't know if you're going to get an even number of reds or whites, so it's very, very random, which means that it has very high entropy. And entropy, we represent it by S. And a change in entropy would look like a delta S or a triangle S, which we already know because we've been dealing with change and deltas all second semester. So if I have the three states of matter, solid, liquid, gas, where do you think entropy is going to be the greatest, or the random is increasing? If you guess gases, you are absolutely correct. Gases have the greatest entropy. So when we are dealing with chemical reactions, usually there's a change in entropy. And luckily, the formula for change in entropy is going to be the same as the change in enthalpy, except we use S's. Delta S equals S of the products minus S of the reactants. And what's really important when we're looking at entropy is to figure out whether entropy is increasing or decreasing. Okay, in the universe, we have laws, or in science we have laws, and it tells us that the entropy in the universe is always increasing. Though this world has an extreme order, however, it's gradually moving towards more disorder. So the universe entropy is always increasing, becoming more and more disordered. The second law of thermodynamics tells us that in any spontaneous process, the overall entropy of the universe is always increasing. There's a good chart on page 760 if you want to reference your textbook on the second law of thermodynamics specifically. Okay, so now we're going to talk about which direction is favored. Okay, is a chemical reaction favoring the products or favoring the reactants? Okay, but we need to look at the extent of the reaction or the speed of the reaction first. Okay, we know that there's an inherent direction for a reaction to proceed. Okay, like the rusting of iron. Once you leave iron out in the elements and it gets oxidized, you cannot go back. It's going to naturally proceed to become rusting. So the rusting of iron occurs without intervention. Okay, without intervention. So we call that spontaneous. Can a spontaneous reaction be reversible on its own? So if that rusty iron were left out and we wanted to take the rust off, can the rust magically happen on its own? The rust removal happen on its own? Okay? No, it can't. You would need to do something for that rusting of iron to be reversible. Okay, so spontaneous reactions cannot be reversible on their own. Well, can we measure the energy transferred in chemical and physical properties, or the measure of heat? Yeah, we just learned that. That's the definition of enthalpy, okay, which is H. The definition of enthalpy tells us that delta H, or the change in heat, can be calculated by taking the heat of the products minus heat of the reactants. In an exothermic reaction, delta H we learned is negative. Why? Because you lose energy. Energy is as heat is going to be given off in the reaction. So what is an endothermic reaction? Why is that positive? Because you need to add heat during the reaction. It cannot proceed on its own without the implement of heat. Okay, let's think of an ice cube. If I have an ice cube and I put it at room temperature, it's going to change, right? It's going to start melting. Do I need to do anything to that ice cube in order for the reaction to start? Yes, I do. Okay, what do I need to do? It's an endothermic reaction. I need to add heat. So when I take that ice cube out and I put it on your desk, it will start reacting. Those bonds will start breaking and you will change the solid ice cube to liquid water because I've added heat to the reactant. Okay, so which one is more ordered or organized? The ice cube or the water? The ice cube. It is a solid, which means that the entropy is at its lowest. Okay, so if we think about that for a minute, the endothermic reaction, and for it to be spontaneous, the products must be more disordered than the reactants. I'm going to say that one more time. For an endothermic reaction to be spontaneous, the products must be more disordered than the reactants. Take that ice cube example. Okay, that ice cube example, the products were liquid, the reactants were solid, which means that the products were more disordered than the reactants. Okay, so how do we measure disorder? How do we measure randomness? Okay, we can measure it as entropy, as S. Because entropy is a quantitative measure of disorder. The larger the S, or the larger the entropy, the greater the disorder. So if I take a look at this picture up here of a solid, liquid, and gas, based on how those particles are arranged, which one do you think has the greatest disorder? I hope you said gas, because a gas has the greatest randomness, the greatest disorder. So the gas has the highest entropy. And then we go to liquid, and then we go to solid. The solid has the lowest entropy. Here's the equation for entropy. Delta S, which is change in entropy, equals entropy of the products minus entropy of the reactants. Okay, so what can you tell me when the delta S, when the products have more entropy than the reactants? Is it positive or negative? Well, if the products have more entropy, that number is going to be larger. Okay, so if I have a bigger number like 4, let's say, minus 3, that's going to equal positive 1. So it's going to be positive when delta S of the products, when S of the products is larger than S of the reactants. So that means that if entropy is increasing, do the products or reactants have more disorder? The products. Because if entropy is increasing, that means that my S of the products is increasing because it would be positive, meaning the products have more disorder. Okay, so if gases are formed from liquids and solids, think about this for a minute. If gases are formed from liquids and solids, is delta S positive or negative? They're positive. You're getting more disorder. Think about it. Gases have more entropy or more disorder than liquids and solids, right? So if that would mean that my products, if gases are the products, my SP is bigger than my S of the reactants, making my delta S positive. If we form a solution from a liquid or a solid, okay, is delta S positive or negative? When you form a solution from a liquid or a solid, you are becoming more random, more disordered. So your delta S is going to be positive because your product, which in this case is your solution, has more randomness than the reactants would. Okay, what about decomposition reactions? Let's think about it. Decomposition reactions mean that you take something, a big component or a big compound, and you break it up into its smaller pieces. Delta S is positive. Okay, the products have more disorder. You've broken it up into smaller pieces instead of one large compound. Okay, so my SP is going to be bigger, remember, delta S equals S of the products minus S of the reactants. This is going to be positive in a decomposition reaction because my products have more entropy than my reactants. Okay, well, what happens if I increase the temperature? Let's see, if I increase the temperature, that means that my products are going to be more random, right? My product is going to have more entropy, so delta S is going to be positive. Can you think of an example when delta S would be negative, or my reactants would have more entropy than my products? I would say go backwards. Two gases react to form a solid. You are getting something that has very much randomness and a lot of disorder, making something that is more orderly and more organized. That would give you a negative delta S. So how does this help us to figure out if a reaction is spontaneous? Okay, well, the second law of thermodynamics tells us that in any spontaneous process, the overall entropy of the universe always increases. So any natural process is tending to move toward a state of greater disorder. Okay? In order to calculate delta S for the universe, we need to know the delta S for the reaction as well as the delta S for the surroundings. So if you wanted to figure out the entropy of the universe, you would use this reaction. You add up all the reaction that we're talking about plus all the delta S of the surroundings, and that's going to give you your entropy of the universe. Free energy, something cool about something being spontaneous. Okay, so there was a scientist with the last name of Gibbs. He came up with Gibbs free energy. So of course, since he discovered it, he made the symbol delta G. Okay, and delta G, Gibbs free energy, is something that when you have a reaction that gives off energy, that energy is free. We can use that energy. We call that Gibbs free energy, and he came up with this reaction, or this equation: delta G equals change in heat minus temperature times change in entropy. And scientists discovered that if this answer is negative, if my delta G is negative, the reaction is spontaneous, it's going to proceed on its own. If my delta G is positive, the reaction isn't spontaneous and I need an input of energy to proceed. If delta G is 0, the reaction's at equilibrium and there's no energy for me to use. Okay, Gibbs free energy is an example of propane. And if you're camping and you have propane gas in your in a tank hooked up to a barbecue, and you turn on that barbecue, you're reacting that propane with the oxygen that's in the environment and in the air, and it's creating heat. It's creating a spontaneous reaction, so it'll create a flame, but it's going to produce carbon dioxide, it's going to produce water, and it's also going to produce heat. That heat is free energy, and we use that heat to grill our food, grill our burgers, and our hot dogs. Okay, that's an example of Gibbs free energy, where we can use kind of a byproduct of a reaction happening. Okay, for your quiz, I've put up this study guide. I'm not sure if I'm going to give you one quiz or a test on this, but this will give you some ideas for you to know. The diagram review is that diagram that I said was on page, I believe, 760 of your textbook. Okay, so in textbook. So you might want to take a look at that before your assessment. And that's all we have for chapter 23.